Hello, class. Welcome to my third attempt at going over the lecture video for Module 3, Fixed Effects. Uh, I'm going to go through this fairly quickly. I had previously done this, and both times there was issues where the audio did not go on. So forgive me if this is going over this fairly fast. If you have any clarification questions, let me know. But just wanted to provide some context. So welcome back, Module 3, Week 3, going over fixed effects modules. We're going to be discussing what they're for, how they're beneficial, when we can tell if they're going to be the proper fit for our circumstances. And with that, we're going to demonstrate a few different ways of um, setting up our model. So we're going to look at our basic OLS model, a pooled OLS model, a demeaned OLS model, and then finally our fixed effects model. We'll be introducing you to a new package this week called the PLM package, Panel Linear Model Package. And yeah, let's get off to the races. There is some additional materials this week you can go through and work on. I won't be going over this one, although I do recommend you go through it and read it. A lot of it is synonymous and in line with what's in the lecture. Some of the visualizations are just a little different in terms of how it demonstrates the some of the varying components we'll learn about fixed effect models. So do read through this on your own. There's some other ones that you don't necessarily need to go through. If you want to be ambitious, you can. But for our purposes for the lab, the lecture, and this will cover everything that you need. Okay, let's jump in. So fixed effect models, they're very helpful, and I'm going to give you the preface at the beginning. They're very helpful if you have groups of data, so multiple groups, with each group having different observations over time. So let's say you've got 5 groups, you've got 5 years worth of data, so you have five observations representing each year, the values for those years, and then you have your groups. Well, actually, let me pull over. So it's going to be called panel data. So I'm going to jump into this one here, and I'm going to show you first. So panel data is going to look like this. You've got your group with different observations ordered in such a way. So usually we'll be working with multiple groups in a real life scenario, multiple groups, multiple times, and then values within each of those times. So this term panel data, just know that that is what this is referring to. It's referring to having your data arranged in such a way that it's grouped by the group that we're working with. And then there's very observations over different periods of time for each group. Okay. So jumping into it, you will need the PLM package and then Stargazer as always. So let's talk about a situation where we want to look at the impact of international aid funding on economic growth. In this example here, we have 3 different countries, country A, B, and C. If we were to look at this and try and determine the relationship between economic growth, and we'll say that our X here is going to be our aid. I don't know why that's not included, so I'll just put it in there. That's going to be our aid. We may determine based on just these values that there's actually a negative relationship. So the more international aid you get, the lower your economic growth is going to be. Our intuition is probably going to tell us that that doesn't seem totally accurate, but this is how the models could give us the wrong estimate or the wrong effect. So this would be the difference between cross-sectional data and panel data. So again, we want to work with the panel data arranged by groups with different observations over time within each group. So let's look at it this way. If we had, let's say those first dots were just year 1 or time 1, uh, if we were to just look at time 1 and look at the difference between the between group variation in the time 1, we would see a negative trend, that there is a negative relationship between economic growth and international aid funding. But if we were to transition that and we were to look within each group and across time, we would now begin to see that there is a positive relationship. So that's ultimately what fixed effects are going to help us to do. They're ultimately going to allow us to look at the change happening within groups, excuse me, while controlling for what's called time invariant changes. These are things that do not change over time. And we'll be harping on that quite a bit throughout this lecture. So we want to look across country, excuse me, if we look across countries, it appears to be negative, which is again here. If we look within countries, it's a positive slope. Now, Simpson's paradox, so this is a statistical phenomenon that says that the trends we identify may be different depending on whether our data is observed in groups or at the aggregate level. So by aggregating our data, I guess technically disaggregating our data too, we can identify or cover up, pardon me, we can cover up certain trends that exist. So once again, to recap the fixed effect model, it's going to allow us to uh, control for time invariant characteristics and try and determine the effect within groups of our policy intervention. So we're going to load some data here, and we're going to cover a couple of things. So assuming that all the farms have the same baseline land quality, all the farmers have the same competencies, baseline competencies, our data may look like this. Now, if we have a difference in land quality, which most of the real world data we're going to run into is going to have different starting places. So if we have a land quality issue, let's say that some farmers have more fertile soil, just naturally, adding fertilizer is just going to make their inputs better. But if we have a baseline where for a different group that has a worse starting soil, although fertilizer does still improve the outcome of corn, that's what this measurement is here, it's not as, there's a difference, pardon me. So if we were to look across group, we might notice a downward trend. However, when we look within group, we can see that regardless of those starting places, the intercepts we can still see a positive trend within group. Okay, and that's also the same for land management. Let's say that the competency or baseline competency for land management is different. That would in and of itself create different starting places for different farmers. So a couple of types of bias we want to talk about here is the Matthew effect first. Matthew effect is going to be represented by the concept of the rich get richer. So if you have more resources, you tend to accumulate more resources over time. So another example would be, let's say we've got a tutoring program for math students. If you have a student who comes in who has a higher baseline competency in math, they will end up higher than the student who comes in with a lower baseline competency. Although both would benefit, the student with a higher baseline may benefit more. So once again, easy to remember that by just the rich get richer. Now, the artificial program impact, this is where we interpret that there's an effect, but it's actually due to some outside factors that we didn't account for or control for. And Simpson's paradox, once again, is by aggregating data, we can hide or even reverse some underlying trends. So our pooled model, which we're going to talk a good amount about, that's going to be when we run an OLS and we don't differentiate by group. So instead of counting each of these as distinct groups, we're going to count all the data together and run our model as such. So the model won't differentiate between groups, and it'll draw a conclusion based on all of the data points, assuming it's all one group. And that could be an impact from the Matthew effect. If we say we have an artificial program impact, meaning that the actual effect within group is not great, or it's the neutral part of me or non-existent, because if we have our group variation that we're not accounting for, the pooled model is going to associate all these as within the same group essentially, and it would tell us that there's an effect when really when you look at the impact within each group, there's no effect. So that's another way. And then the Simpsons paradox is ultimately that you get the wrong sign. So we see that we actually, if we looked within each group, we'd have an effect. However, when we run a pooled model, not differentiating by group, it would show us the reverse. It would show us that there's a negative effect rather than a positive effect. So we're going to talk about OLS, demeaning, and fixed effects, which I'll tell you now, demeaning and running an OLS with demean data is the same as a fixed effect model. So we'll go over demeaning just to give you a big picture. We go through that because it's just showing another way of getting fixed effects, but sort of superfluous, but that's sort of a way that we can account for between group variation, or excuse me, time invariant characteristics. Okay, so moving in, we're going to continue with the international aid and economic growth concept. We have some data we're going to load here, visually plotted out. We see each country. We can see a trend that there's positive slope with more international aid means higher economic growth. Let's first run it by looking at just 1 year of data and doing a basic OLS model. We plot it out here first. It looks a lot like our original model. We can see that there appears to be a negative trend. And so by subsetting our data to where we only get the time value of 1, so the first time value for these countries, and we run our model this way, this is going to give us a impact of a negative impact, where for the more international aid funding you get, the lower your economic growth would be. So keep this in mind. We're going to look at it a few times here, but just recall that. Then we run a pooled OLS model, which is going to be the same basic model, except we're not going to be subsetting for just a year one. So it's going to go back. It's still not accounting for groups, but it's still going to be counting all the data. So once again, no differentiating by group. We just run the outcome of X on Y. And we can see here that if we run it this way, it's going to give us a neutral effect. There's no statistically significant effect. And so a key thing to keep in mind is if you have data that has no groups, a pooled OLS model can be unbiased and efficient. So if you're working with one group, pooled models are great. They're going to do fine for you. However, if you do a pooled model with data with groups, you're going to have a biased and inefficient model. And that goes back to what we were looking at before. It's going to misinterpret or miscalculate, improperly estimate our program effect. So moving into some of the demeaning data components, we have no groups in the data. We just have our baseline, our average of X and Y. If we have data with groups, you want to have the average for each group. So then data with no groups once again. And then this is the demeaning. This is another way of saying mean centering, where you take the value of X and you subtract it by the average of X. And then you do this for each observation. So as we discussed, the OLS, it can be problematic if you're working with panel data, which is the data as seen here, where you have observations, you have it grouped and at different points in time. So demeaning is simply the way of removing a cross-country variation. So the fixed effect model helps to account for the time invariant characteristics. This demeaning process is helping us to remove, excuse me, to end up plotting everything on the same line. So if you take your observation of X, you subtract it by the average of all the X values. So we have 2 as our observation. The average of X values is 4. We get our demeaned X value of -2. You do this for all of your variables, and it ultimately gets you to a point where you've demeaned your data and you've put them on the same line. And if we were just working with a pooled model, we would have it all together here. But when we demean it, it allows us to place it all together to where at this point, if you have demeaned data, you can run a basic OLS model. So if we were to do this, we can see now with a demeaned OLS model, we actually now get a statistically significant positive effect of international aid on economic growth. So we have 3 different models here. We're going to get into at the very end a way to test to see which model is the most accurate. But one fundamental thing you want to keep in mind is if you're working with data that consists of observations over time among different groups, a basic pooled model, not accounting for those groups, is going to give you improper estimates. Okay, so that's the fundamental for this. So demeaning is going to tell us the within country differences, which is what we want to see. Now moving into the fixed effect model. So ultimately the fixed effect model is just an OLS that includes a set of dummy variables differentiating each group. So in the case of our countries, we would want a dummy variable, 3 dummy variables, and it would be one for each country. Now, when we run this, the model is going to automatically drop one of those dummy variables. So the first group is going to be dropped, and it's just going to be considered the intercept. And I believe we went over that, or you saw that in last week's diff and diff lab. So just keep that in mind, or excuse me, I believe that was in the PowerPoint for last week's diff and diff lab. So the first intercept, or the constant that we get, that's going to actually be the intercept of our first country. Every other country intercept or coefficient after that is going to represent the change to the change or the difference between the first country's intercept, which is our constant, and the that country's coefficient. So you'll see that more visually here. And this is ultimately going to give us the same result as the demeaned OLS data. So we can see our R code here. We have our fixed regression model. It's going to look very similar, except we're going to be including a factored group component. So as that factor G, G represented our groups. So this is establishing that each different value in the G column is going to be a different group. Run this here. And so we have our original OLS looking at just the first year of data, gives us the illusion of a negative trend. We have all of our data combined into one, where it's assumed with the pooled OLS model that it's all the same data, or it's all the same group. That gives us a non-statistically significant but positive effect. And then we have our demeaned OLS, where we have a statistically significant positive effect. And finally, our fixed regression, which we just ran. Here, once again, same thing as a pooled model, except we're going to be adding a group dummy variable. So we can see that we have a constant, as mentioned before. This is actually the country A, because it's dropped, and then it becomes the intercept. And then we have our country B and C coefficients. These represent the difference between country B's intercept and country A, and then country C's intercept and country A. And our coefficient itself for international aid is going to be the same as our D mean OLS, because mathematically they're doing the same thing. Moving more into the statistical model, it's once again using panel data. We have some faux data here. It doesn't actually have any context, but we're looking at multiple observations over time within each entity. So for group one, or for each group, excuse me, which we have 7 groups, we have 5 years of observation, so 5 observations per group. So that gives us a total of 35 observations, 5 times 7. Now we're interested in investigating the effect of X on our outcome variable. So X is going to be our policy variable, and then we have our outcome variable just listed as this outcome. Y represents our time. So I know sometimes we move those around, just know what each represents. Now, because these groups are going to be different between, so the between variation, all the groups are different, an OLS model is going to give us a improper result or an improper estimate of our effect. So we want to control for those things. So let's look again. If we do a pooled model, it's not going to differentiate between the different groups. It's going to assume all of it is essentially one group, and it's going to derive a conclusion based on that. But we know we're working with 7 different groups. So we need to make sure that we're using the correct model for that. So we want to control for the between group variation and make sure that we're only estimating the effects within each group. So if we look at it this way, we color code each group, we can see each one has a different intercept. So we want to make sure we're controlling for that. Getting into the actual statistical model itself, we have our outcome variable, so YIT, where I is going to be representing the number of groups in the dataset. T is going to be representing the number of time periods in the dataset. And then we have our beta 1, which this is our policy variable. That's going to indicate the average changes in the outcome over time within each group. We'll say it again. This will tell us the within group change. So it is not going to be representative of each individual group's change. It's going to be the average changes within each group. Then we have our A1, alpha 1, I always forget what that's called. I think it's alpha, is a set of dummy variables for each entity, and then our error term as usual. Now I want to point this out. This is the same as before, where we simply factor our groups, but this includes a -1. And the reason that is it just gives us a intercept for each group rather than a constant for or an intercept for group 1, and then changes to that intercept for the coefficients representing each country. So now it's just going to give us an actual intercept for each group. Okay, so we have our policy variable effect, and then we have the intercept for each group. You guys can ignore this. That's just talking about the PLM function. That was from a previous recording that had no audio. Uh, okay, so let's move on here. And this section just explains what the -1 does in this situation. So now we have a single slope for all of the groups. However, we have different intercepts. So again, this slope isn't going to tell us each individual group's slope. It's going to tell us the overall slope within groups. So the average intercept, excuse me, the intercept represents the average of each group when international aid is equal to 0. And this fixed effect model, it better approximates the actual structure of the data, and it does control for the group level characteristics. So the dummy variables in and of themselves are controlling for the time invariant characteristics, like the demeaning that helps to that controls for the time invariant characteristics. So does adding dummy variables. They essentially do the same thing just by accomplishing them in a slightly different way. It does not control for characteristics though that change over time. So if you have something like your location, your ethnicity, things along those lines don't change over time. And so the model, including the dummy variables, this controls for those items. It does not control though for things that do change over time, like perhaps um, income, age, marital status, things of that nature. All right, so moving on, let's talk about a different example. Let's say we want to look at the investment of the government spending, excuse me, on research and development as our policy variable, and then we want to see how that affects private companies' investments into R&D. Okay, so our policy variable is going to be our public investment into R&D, and our outcome variable is going to be private sector investment into R&D. We have a panel data set. It's going to consist of 10 companies and observations over a 5-year period. So there's 5 observations per company, and you can see that here. And sometimes everybody, again, in the real world, the data is not necessarily going to come clean and tidy, ready to rock and roll. I did my capstone actually in December of 2024, well, the fall semester of 2024, and I worked with the city of Phoenix where we had some very messy data, but it was different HOAs. We were evaluating a homeowner association water efficiency program, so a program where they would work with HOAs specifically to try and figure out ways to reduce their water use on things like landscaping primarily. And so that data came to me, and it was pretty, what's the word? Well, it was not tidy, I'll say that. And so a significant part of the time that we'll be spending, or you'll have to spend in the real world, maybe on actually cleaning and arranging your data in such a way that it is in panel format. So just something to keep in mind. It's not always going to come to you all clean and pretty and tidy. So we know that each company has different levels of investment. So now we're going to look at some box and whisker plots to see the variation between groups. So we have down here, each box and whisker is going to represent excuse me, our company, each company, and then the range of their R&D investment. So we can see some companies have a fairly narrow, at least in comparison to others, range of investment, and some have pretty wide ranges. So we know that there's a lot of between group variation we want to make sure we're accounting for. If we look at it each year, and we can see that over the years, if we aggregate the groups and look at the changes over years, we can see the variation of investment over the years. Now, keep in mind to remind you, heterogeneity, you should be familiar with this term, but it's going to refer to the differences across the groups that can affect our outcome variables. So that can tie back to the types of bias earlier that we talked about. So we look at this again in a line graph. We can see the trends over the 5-year period. Some are tight, some have wide ranges. So because of those differences across the companies, we want to use a fixed effect because that will control for those unobserved characteristics. So once again, this is going to point us in the direction of a fixed effect model. Let's go through this and let's run an OLS and we'll compare it once again. So we have our data, we have our policy variable, public investment of research and development on private investment. We run that and we see that we get a coefficient of 90.92. So that's saying that for every dollar invested by the government, public or the private sector will spend about 92 cents on research and development. So if we were to plot this, we know that this pooled model, it does not account for group differences. So it's just looking at all the data as if it were one single group and plotting our model based on that. However, if we do a grouped OLS, this is also known as just a dummy variable OLS, where we do the same thing and simply include the dummy variable component set as factored to our group. That will assign a different level for each different value in our company or group column, whatever it is it's labeled as. And that will allow us to create dummy variables. We can rerun this. And once again, we get our constant being represented by, or sorry, our company one intercept being represented by our constant. So this is the actual intercept. And then we have the value of the value of the policy variable coefficient. So now it's saying comparative to our um, OLS without dummy variables, it was 92 cents. So for every dollar invested by the government, private sector would spend 92 cents. Here we have the new estimate, excuse me, as $1.15. So for every dollar invested by the government, we get a $1.15 investment by the companies. Now I want to delete this because that could be confusing for everybody. As mentioned previously, not going to let me delete it. Oh, you just got to see that your instructor clearly doesn't know how to use uh, Adobe. So let's just go ahead and ignore that part. Yeah, ignore these notes here. So this is without demeaning, but I want to reemphasize what I previously told you. Demeaning the data and running a basic OLS is going to produce the same results as including a dummy variable within our OLS. Okay, so both of them do account, or sorry, control for the time invariant heterogeneity by doing it in different ways. So the dummy variable OLS controls for it, and the demeaning, then running a basic OLS controls for it. Okay. So this shows a more positive impact than our previous OLS, and we have our different coefficients here for the countries. So we know that each has an intercept if they all share the same slope, because once again, that's taking into consideration the average slope within group. We plot this, so we have each different intercept, we have each with a slope, and then we have our general model line. Now I want to introduce you to the PLM package. This is what you'll be using in your lab today, sorry, this week. A couple things I want to tell you. So you will have to download the PLM package, and it's going to work very similar to how the LM model works or the LM function works. But there's two parts that you want to keep in mind. One, you have to establish an index. So the index is the group. So the group that you want to use for your model, how you're grouping your data. And then model determines if we're going to either do within or random. So random effects is something we'll talk about at the very end. When we do a fixed effect model, we want to use index to select or designate our group. And then we want to set model to within. So that way we're looking at the within group variation, not random effects, which we'll touch on at the very end. You'll notice shortly too that if you leave model out, if you're running a fixed effect model, you can leave this out and it will default with the assumption that you're wanting to do a fixed effect model. Okay. So just something to keep in mind there too. So we have our OLS model, our dummy variable OLS model, and we have our fixed effect model. We can see that the dummy variable model and the fixed effect model itself, they both produce the same coefficient because they're both essentially doing the same thing. Fixed effects is going to be essentially demeaning all of the data. And that's what, so that both of these do mathematically, fixed effect and demeaning, OLS, they do the same thing mathematically. And the OLS with dummies, it accounts for the uh, time invariant changes or time invariant characteristics by just associating each group as its own group. And you'll notice there's no coefficients for intercept for the fixed effect model. And that's because we can use the fixEF function in order to print each intercept. So as you can see, fixEF and then the object you saved your model to, we just designated it as fixed. Okay. And now, if we're ever wondering which model is going to be the best, because there are some differences, we always want to check and see if the pooled model, or excuse me, the OLS model itself, the pooled OLS model, pardon me, is going to be better than our fixed effect. And the way you can do this is with a built-in function in the PLM package, where you can run PF_test, include your two data frames, or your objects, your fixed effect model object, as well as your OLS object. And if the output, it tests for, excuse me, if the output produces a value less than 0.05, then you know that your fixed effect model is the best option. So a couple final points on fixed effects. So a fixed effect model will allow us to control for time invariant characteristics of an entity. And these even accounts for characteristics that we cannot measure or observe. So this is why it's so powerful. It can get rid of some of that noise that we can't even tell is there. Now, this as an assumption that we assume that some of these unobserved characteristics are correlated with our outcome and our policy. So visually, this might remind you all of it. I believe it was in one of your previous classes. You go over it. Sorry, I believe passing over it. There we go. So when we have a variable that is both correlated with our outcome and our policy variable, or our treatment and our outcome, it absorbs some of that and it can lead to omitted variable bias. Fixed effects account for these unobserved omitted variables, and it helps us to get a more accurate picture. So when we do a fixed effect, we are assuming that there are some omitted variables that are correlated with both our outcome and our policy variable. So we use a fixed effect to control for those things. So ultimately, it's going to control for those time invariant characteristics, and this reduces our omitted variable bias issues. Now, when we run a fixed effect, this will not allow us to investigate time invariant characteristics, those that we are explicitly controlling for. We will not be able to see their effect because it blocks those or drops those, as we'll see in the following section. So essentially, a fixed effect is going to absorb these time invariant characteristics. So you won't get a coefficient for them, and therefore you won't be able to determine their impact at all. And now it is also going to be within our fixed effect an assumption that we're assuming each entity is unique and different. So that's meaning, and let me preface this, this is important to distinguish between fixed effect and random effects. So remember this part to differentiate. So fixed effects does assume that each entity is unique, and that means that those error terms and each entity's constant are not correlated with other entities' terms and constant. So let me put that again back here for you. So if we have an omitted variable that's correlated with both our outcome variable and our policy variable, this is what we're trying to control for. So we are assuming when we do a fixed effect that there are variables such as this that will be correlated with both. When we get to the random effects, we would use a random effects model if we assumed that it was not correlated with our policy variable. If it wasn't correlated with our policy variable, then we wouldn't want to do a random, excuse me, if it's correlated with our policy variable, if we make the assumption that it would be, then we would use a fixed effect. If we don't assume that it is, then we would not use a fixed effect and instead use a random effect. And again, we'll cover random effects at the very end. When you get to that point, though, general rule is to do both a fixed effect and a random effect, pardon me, and then you can test that using a Hausman test, which we will see at the very end of this. All right, let's do this replication. So we're going to be looking at something that's called deterrence theory, and that's ultimately saying that if the certainty of punishment, when we're talking about crimes, and the severity of that punishment, both of those things will lead to a change in crime. So if there's a increased certainty of being punished for a crime and an increased severity of that punishment, then that would deter crime. There's some debate about this, but that's ultimately what we're looking at here. So we're going to have a panel data set, 90 observations, 90 counties, 90 groups. We have time frame ranging from 1981 to 1987. So our hypothesis will be that based on deterrence theory, we argue that the greater the certainty or severity of pain will decrease crime in a given country. And you can actually do this yourself using the data within the PLM package. If you do data crime, load that in. We can see some of the data here. We have our groups, our dummy variables listed here for groups. We have the time itself, and then we have our different values. So we have crime, we have the probability of arrest, we have the probability of conviction, probability of prison sentence, and then the average sentencing. So we have some of our basic information here. We also have some additional controls. I highlight these because I just want you to keep these in mind um, for when we look at our coefficients. So we have the counties included in a metropolitan area, county location, and then the percentage minority. And so think about it for just a second. Why would I indicate those? What using a fixed effect model, what do you think may happen to or not happen at all to these? Well, if you thought about it, we'll see here shortly. We have two different models we've run. We have our basic OLS model here, where we have everything included using the LM function. And then we have our panel linear model function. And again, we want to set the index to county. You'll notice that model equals within, because this is a fixed effect model. And for fixed effect models, we set it to within. It's not included. That's because the default here is that that is the default for a PLM function. If there's no within included, then it's just going to assume, or sorry, no model equals included. It will assume that it is a within model or a fixed effect model. And you would change that when you do a random effect. And then we have our index set. So this is establishing the group we're going to be differentiating by. And we have that set as county. Okay, looking at our coefficient tables, we have our intercept here, which is the first group. And then we have our actual coefficients for the probability of arrest. This is one I really want to focus on, both of which are negative and statistically significant. However, the OLS model estimates the impact of the probability of arrest at a threefold of what our fixed effect model does. And once again, that ties back to what we saw at the very beginning of our lecture, where we noticed that there was a sort of a Matthew effect, or when you do a pooled effect and not differentiate by group, it can overestimate the effect itself. And then we have some other items here I'll get into, but the ones I wanted to think about more as well is, as I asked you before, why are these not listed? The fixed effect model, as we discussed, it absorbs or controls for and drops time invariant characteristics. So even though we included those in our model, the models include all the same variables. These were dropped because they were time invariant. They didn't change. So these are locations. These locations didn't change, and then the percentage minority. So these values didn't change over time within our observation, and so these are dropped from the model itself. So we can see when we do the pool model, it does overestimate the impact by a large factor, by about 300%. And another thing to look for too, and this is where we have to pay close attention, is that the length of prison sentences, that coefficient was positively related to crime. So we got to use our brains here and be cautious, because we know that time variant omitted variable, whoa, goodness gracious, time variant omitted variable bias can still exist. It can still affect our results. And so it wouldn't make sense that people that aren't planning to commit crime would then decide to, just because they learned that prison sentences were longer. So it's likely that some other unaccounted for component affected that. So things something like increases in crime for other reasons were already taking place. So there was already increased sentencing taking place. So there's some intuition and logic that would go into interpreting these as well. Okay, and then like we saw before, to print our intercepts for each group, we can do the fix EF function. And we know that the variables are time invariant, like we mentioned. So region, type, location, those other ones I already showed you. The reasons those are dropped is because they're time invariant, and the model itself drops those out in controls for those. And that's why we also can't measure those directly with a fixed effect model. Okay, now if we want to check and see what's better, the OLS model or the fixed effect model, we once again can use the PF test. And we do that by including PF test. We do our OLS model, how we saved it, and our fixed effect model, how we saved it. If it's less than 0.05, we know we keep the fixed effect model, which we know that it is. Now, finally, to wrap this up, we're going to be doing the random effects. So random effects is sort of the opposite of fixed effects in that we know that fixed effect, it's assuming that there's no correlation across entities, error terms, and constants. Again, we think that each entity is independent from the other. Now, this assumption, it can be tested by using a random effects model. And this is where we assume that the differences across entities, they influence our dependent variable, and there is correlation across entities, error terms, and constraints. So we're going to stick with that previous example about R&D, and we're going to use our PLM function, remembering to set model to random. And now just a little thought-provoking exercise here. Um, the previous models, they only did index equals company. So think about it a little bit, and you don't need to tell me, but just ponder on it. Why would we need to include index for both company and year in a random effects model? Okay. All right, and then we run it, and let's see what we got here. So we've got $1.10. So off off the cuff, we'd be able to see that for every dollar invested by the public, the private companies would spend about $1.10 on research and development. But now we want to keep in mind when we interpret a fixed effect coefficient, we're able to determine that the policy variable coefficient is the average within group change. However, when we're looking at a random effects model, this is incorporating within entity and between entity effects. So we just have to keep that in mind when we're that it's not just a within group effect, it's the overall data set. So we want to keep that in mind when we're focusing on our interpretation. And as I mentioned before, there's tests to determine if a random or a fixed effect model is going to be um, the best for us. And we would do that with the Hausman test, which is just going to be the pH test. You include your fixed effect model, your random effects model, and then you would see if it's less than the 0.05. If so, we know that the fixed effect is going to be our best bet. So a couple last notes on the random effects. So random effects, this is going to allow us to include time invariant characteristics. And remember, fixed effects allows us to control for time invariant characteristics, taking them out of the equation, while random effects is intentionally including those. And that's because we make the assumption that there's no correlation between the predictor and the error terms. So once again, going back to the slide, my little beautiful red circle here, we're assuming that they're not correlated, where in this case, the omitted variable bias, where it's correlating with our policy variable, this would be a fixed effect. We would do a random effects if we assume that it's not correlated there. Okay. And then when we're doing a random effects, we do want to be very cautious because it's not automatically controlling for those. So since we're not doing dummy variables, we want to make sure that we are specifying our controls. And then last, general practice or general rule is fixed effects will most of the time be a better model, but run both and do the Hausman test, and you can confirm that. That's it for the lecture, folks. If you have any questions, as always, reach out. Read through this component here as well, the correcting bias with panel data presentation. Most of this is sort of repetitive or redundant from what we already learned, but it does offer the information in a slightly different visual format. And then last, I am at least for this week, I am determining to not run a code through within or for the lab. And the reason I've done that is I am hesitant that the code throughs for the lab, well, let me backtrack. The labs are so straightforward in how to accomplish them after you read the lecture, unlike some other classes where the lectures aren't as clear with the lab. They don't translate as well. I feel like this course is set up to where it does. All that being said, I don't want to give you the answers or make it too easy because I do think you need to exercise some of those intelligence muscles and you can go back and forth and sort of wrestle with the lecture and the presentation to complete the labs. So I'm going to forego doing a code through. It's very straightforward. I will review the lab with you here. It's 4 questions worth 100 points plus some bonus points as usual. Ultimately, we're going to be looking at beer taxes and seeing if they negatively affect car accidents at nighttime. You have your data you can load up, and then you're just going to be asking some questions. So you will need to work on doing a pooled model first, and then you're going to be working on doing a fixed effect model. You're going to discuss the differences, and then you're going to also review why certain variables should or should not be included in a fixed effect model or what would happen to those. And then the bonus question will be discussing some of the demeaning if you wish to pursue that. As always, if you have any issues, questions, post on GitHub, and I will be available for office hours if you need additional support. But that's it for this week, folks. Thank you so much for your time. Have a great week and good luck on the assignment. We'll see you for Module 4.